Okay, finally, let's talk about active transport. Active transport, like I said before, has kind of this difference between passive transport in the fact that you need energy and you're going from a low concentration to a high concentration. So if you're going from low, here's your car, to high, you're going to have to start the engine. You're going to have to burn through some gasoline to get it to go there. So we've got basically three types of active transport. Primary active transport, okay, means that we are actually getting ATP, breaking it down, and then using the energy that we've gotten from that ATP to move something against its concentration gradient. Movement is often dependent on how many pumps are available, but the pump itself has to have at least two binding sites, one for the ATP and one for the thing being moved. So if you look over here, ATP has its own individual binding site because once I break this ATP and I end up with ADP and phosphate, pretty much what that means is I've charged this little transport protein up. It's kind of like charging your phone. Yes, you have to plug it in, but then once it's charged up, then you can use it as you will. So with primary active transport, you use ATP directly and you break it down directly. Okay, secondary active transport. Um, Secondary active transport still needs energy, but secondary active transport kind of uses a secondary way of making ATP. So, windmills. Why do we have windmills? Are we harvesting wind and putting it in jars and selling it to people? No. What we're doing is we're using something that's already there, the wind, to turn the turbine of that windmill to basically power a generator, right? So we're using something that's free to get something that you want. With secondary active transport, you're basically doing the same thing. So you're moving one thing with its concentration gradient. Let me get a better color. You're moving one thing with its concentration gradient. So it's high here and it's low here. And as you move this, think about that turbine on a windmill. This starts charging this up. Okay? Now that it's charged up, I can move something against its concentration gradient. I've got 3 glucose here, 1 glucose there. 1, 3, 3 is the bigger number. It should be going the other direction. But because I've got that extra energy from moving the high amount of sodium, I'm able to actually move this. We call it secondary because unlike primary, I'm not using ATP directly. I'm using the passive transport of one thing to energize my carrier, and then using that energy that I've created to move something against its concentration gradient. So again, secondary active transport, it's not ATP direct. Okay? Now, vesicular transport. Remember, vesicular is just a very fancy way of saying bubble. Okay? So, when I want to move large volumes or large objects across the plasma membrane, I can do this through the formation of a bubble into my cell membrane, which you can see here. Okay, get a better color again. Here, you can see that membrane kind of start to invaginate. It's actually starting to make a little culvert here, and it keeps making that culvert until eventually it pinches off and makes this bubble. That's vesicular transport. I am transporting a large volume. It's not about making a doorway that opens and closes. It's not about doing anything like that. It's literally, I'm going to surround this thing and bring it inside. Now, this does cost ATP. So it is still a type of active transport because I'm still going against a concentration gradient. Now, something else that's kind of interesting with our channels being involved, movement is very specific. Only one thing can go through this channel. We talked about the specificity when we talked about transport proteins. With vesicular transport, if you fit in the bubble, you go. So the specificity that is seen in other types of transport is not really seen here. If it happens to float into that bubble that I'm making, it goes, period, whether I want it to or not. We actually have two main types of vesicular transport. We have endocytosis and we have exocytosis. In endocytosis, we have three options. We've got pinocytosis, phagocytosis, and receptor-mediated endocytosis. So let's talk about those. Pino means to drink. So it is technically still endocytosis, but pretty much the main thing that I'm moving is liquid with stuff that's dissolved in it. I'm not really moving anything solid. So pino, to drink, cyto means cell. So the cell is drinking. And again, it's incoming because it's endocytosis, incoming. Phagocytosis. Phago means to eat. Again, cytocell. So with phagocytosis, we're not just talking about liquid and whatever is just dissolved in it. We're actually talking about something solid, like what you see over here, getting pulled into the cell. We use this quite a bit when we're trying to fight invaders in our body. Our white blood cells eat them. And then once they're inside the white blood cell, that's where we kill it. So we use that method of moving cells, actual cells, which are big and bulky. Now, receptor-mediated endocytosis. Mediate means to control. Remember that. Remember that a receptor is a receiver. It's something that holds on to something else. I just told you that when we do vesicular transport, it costs us ATP. So, with receptor-mediated endocytosis, we're basically trying to make sure that we have enough of what we want that it's worth the ATP we need to spend. So if I told you for every day you come to class, I'll give you a penny, would you show up every single day? Probably not. You'd probably be like, okay, that's like 28 cents. No thanks. Now, if I told you I would give you $100 every day you showed up to class, that's $2,800. I know students who would be like, I'd come to class even if I didn't have it, just to get that $100, right? Why? Because it's worth it. Yeah? Well, in this case, it's kind of the same thing. If you look over here, until I have enough of these little purple spheres, I'm not going to do my endocytosis. Once I do have enough, though, once it's worth the ATP I have to spend, then yes, then I'll do it. But it's controlled by the number of receptors that are being bound to. That's why we call it receptor mediated. Now, exocytosis. Exocytosis is actually the exact opposite. So we create a product inside the cell and we need to get it outside the cell. So if you look, I've created a product, it's in a bubble. I come to my cell membrane and I basically fuse my bubble with the cell membrane so that I can release that product. Exo, exit, it's going out. Again, this is active transport, so it does cost ATP. But I'm packaging something inside my cell and releasing it in a mass amount. It isn't, I'm releasing one molecule or I'm releasing one atom. I'm actually releasing a bulk amount. A lot of our proteins get released this way. Some of our hormones get released this way. So it's a way to kind of mass release a product that we need inside the body, but not inside of our specific cell that made it.